Okay, so hello everyone, and we should step in this video on some basic concepts in optimization that are very useful when it comes to understanding learning algorithms. But before we dive in, let's define optimization. What do we mean when we call the term optimization? So whenever I say optimization, you should think of a function, and you are at random initialization on the surface of that function. And you need to reach a specific point also on the surface of that function. The optimization is answering the question, how should I tweak the parameters starting at my initialization and going to that specific point. So in this example, we are at x squared plus y squared plus 4, and we are seeing how to tweak the parameters in order to reach the global maxima, which will turn out after reaching to be 0, 0, 4. So it's taking small steps, or not necessarily small steps, but it's taking some process to move us from a specific initialization to a specific point via some compute. Why optimization matters in AI? This should be very obvious for you now after finishing week 1. And in week 1 you learned about cost functions, and cost functions are the average over the individual loss functions per example. And what do this mean is cost functions are measuring how bad your predictions are. So we desire a zero cost function theoretically, and cost functions are just a way to measure how far your predictions are from the true labels, from the real world. And we desire to minimize this cost function in machine learning and supervised learning setups. At least a supervised learning system that with the minimal cost function is an accurate and more general system. A useful analogy when it comes to understanding optimization is standing on a top of a hill, and you need to go to the bottom in a systematic but also in the fastest way. So you are standing on the top and you need to go to the bottom. So what we're gonna do is take small steps each time in order to reach the global minimum. But in what direction you should take those steps? It turned out to be that you should take every step in the direction of the steepest decrease. So you are standing on the top of a hill. You should look around and see and identify the steepest decrease, the fastest way that will gonna let you move to the next level on that hill, and then you should go in that direction. And from there, after reaching that level, which will turn out to be a local minima, take another step and go to the lower level, which will turn out to be another local minima. Small local minimas after each other in order to reach the global minima, which will turn out to be the bottom of the hill. Let's take an example and try to build a systematic setup in order to maximize it. So we are at x equal 1 and y equal minus 2 in a function which is nothing but their multiplication, which is x times y. Now the function evaluates to minus 2, and we should define a systematic way to maximize that function. Our strategy, our initial strategy should be a random search. So we're gonna say evaluate x as x plus x prime, where x prime is a random number. And if this turned out to be a candidate for a maximum, take it. If not, just log it. Stay there. And this is really not bad for small circuits, for small functions. But in machine learning, we are talking about some complex functions with many parameters. So what we'll turn out to do is we need a more systematic way in order to increase the value of the function or decrease it in machine learning systematically. So at each iteration, we should increase our performance. So here it comes, and we define gradients, and I should define it in an example. So consider yourself on a surface whose height above sea level at point xy is hxy. So there is a point above sea level which is xy, and its height is the evaluation of the function at x and y. The gradient of h is at a specific point on that surface is a vector, and this vector should point in the direction of the steepest slope. It should point to the maximum of that function, to the maximum of that surface. And the steepness of the slope at that point is given by the magnitude of the gradient vector. So this vector is two things. It's pointing to the maximum of that surface, and the steepness of that pointing or of the slope is nothing but the magnitude of that gradient. Another way to look at gradients is assume you are in this grid, and at each point there is a number which is the temperature. The gradient or the derivative at each point is nothing but a vector pointing to the direction where the temperature rises. Think of the derivative as a force that should be applied to each input, and thus taking the output to a higher level, and thus maximizing the output. So if we tweaked x by the derivative of the function x times y by x, and y by the derivative of the function x times y by y, we should at each time be higher, or be at least higher than the step before us. And now we define gradient descent. And the gradient descent, we have also gradient ascent, but we are not interested in gradient ascent in machine learning. We are interested in gradient descent. And the gradient descent is, we're gonna answer the question, how to reach from a random initialization to the global minima. So we have a random initialization x0, and the gradient descent, we're gonna take small steps in the direction of the global minima, and then converging to that global minima maybe at x4 or after x4 in this figure. Let's apply the gradient descent setup on the linear regression system we have seen in week 1. So in linear regression, we are talking about y hat, which is the evaluation of w times an input x plus b. And for simplicity, let's assume that x is one number. It's not a vector. It's not a feature vector. It's just a one number evaluated by w and b. And let's define a loss function, which is the mean squared error, and the average of these losses is nothing but the cost function, which should be the average of the mean squared errors, individual errors at each data point in our data set. And if we need to find the best w and best b, we should let the cost function converge to a global minima. We should find the w, the parameters w and b, that will gonna minimize or just evaluate the cost function to be the global minimum. The way we're gonna do this is using gradient descent. We should be initialized randomly at some x0 like here, and then we should take small steps in the direction of the global minima, and then converge there. The way we're gonna do this is we need to evaluate d of this cost function with respect to w. So we need the derivative of the cost function with respect to w, and the derivative of the cost function with respect to b at each step in a gradient descent. And then we should take our step in the direction of, we should tweak w in the direction of that gradient, of the gradient of w, and we should tweak b in the direction of the gradient of b. But now we should someone should have the question by how much we should tweak w and b. It turned out that we should also tweak w by the magnitude of the derivative of the cost function with respect to w, and we should tweak b with the derivative of the cost function with respect to b. This is the derivative of the cost function with respect to w and the derivative of the cost function with respect to b. I'm gonna send you a specific sheet where we derive these derivatives, but for now just focus on how we should tweak w and b. So we are tweaking w by minus some learning rate theta that Andrew will gonna touch on so much in his lectures, times the derivative of the cost function with respect to w. So we are going opposite to the gradient. We said that the gradient will gonna point to the maximum of a function. We are going opposite of that gradient, so we are pointing to the minimum of that function. And we said that the slope of that, the steepness of that vector, of that slope is the magnitude of that gradient, so we are tweaking by it. And b is also nothing but, is also should be tweaked by minus some learning rate alpha times the gradient with respect to b. And yeah, that's it. If you have any questions, feel free to DM or just drop it to one of the admins.